Amplitude modulation. Part 1. In this video presentation we will explain the theory and principles of amplitude modulation, one of the three analog modulation processes. Modulation is the process of altering a characteristic of the carrier in accordance with the instantaneous value of the intelligence. In other words, it is the process of impressing information signal onto a high-frequency carrier signal where some properties of the carrier is varied in accordance to the information. The reverse process of the modulation where the received signals are transformed back to their original form is called demodulation. The basic types of analog modulation are amplitude modulation. In this modulation process, the amplitude of the carrier wave is varied in proportion to that of the message signal being transmitted. Frequency modulation is the process of modulation where the instantaneous frequency deviation, the difference between the frequency of the carrier and its center frequency, is proportional to the modulating signal. And phase modulation, which encodes a message signal as variations in the instantaneous phase of a carrier. Note: frequencies that are high enough to be efficiently radiated by an antenna and propagated through free space is called radio frequencies or simply RF. Amplitude modulation is the process of changing the amplitude of a relatively high-frequency carrier signal in proportion with the instantaneous value of the modulating signal. This type of modulation is relatively inexpensive, low quality, used for commercial broadcasting of both audio and video signals. Amplitude modulation is also used for two-way mobile radio communications, such as in citizens band radio. There are several types of amplitude modulation, but AM double sideband full carrier is the most commonly used modulation process for AM. AM double sideband full carrier is also called as conventional AM or simply AM. The AM envelope is the variations of amplitude of an amplitude modulated wave. If a modulating signal Vm is superimposed to a carrier signal Vc using the process of amplitude modulation, an AM modulated wave will result. With no modulation, the amplitude, as well as the frequency, are both constant. With modulation, the amplitude of the carrier varies in accordance with the modulating signal. The frequency still in constant value. An AM modulator is a nonlinear device. Therefore, nonlinear mixing occurs and the output envelope is a complex wave made up of DC voltage, the carrier frequency, and the f of C plus f of m and f of C minus fm, that is the cross products. The figure shows the frequency spectrum of an AM double sideband full carrier wave. The frequency spectrum of an AM wave is composed of the carrier frequency f of C, the lower side frequency, f of C minus f of m max, and the upper side frequency, f of C plus f of m max. The lower sideband is the band of frequencies between the carrier frequency minus the maximum modulating frequency, and any frequency within this band is called a lower side frequency. The upper sideband is the band of frequencies between the carrier frequency plus the maximum modulating frequency, and any frequency within this band is called an upper side frequency. The bandwidth of an AM wave is equal to the highest upper side frequency minus the lowest lower side frequency. This figure shows a three-dimensional plot of the AM wave along with its modulating signal, lower sideband, carrier, and upper sideband signals. One side of the figure shows the amplitude versus time plot of the signals, which is known as time domain plot. On the other side shows the amplitude versus frequency plot of the signals, which is known as frequency domain plot. Coefficient of modulation is a term used to describe the amount of amplitude change or modulation present in an AM waveform. This can be calculated as the ratio of the peak change in the amplitude of the output waveform voltage to the peak amplitude of the unmodulated carrier voltage. The percent modulation is simply the coefficient of modulation multiplied by 100%. The figure shows an AM double sideband full carrier wave. The maximum peak amplitude of this wave is equal to the peak amplitude of the unmodulated carrier voltage plus the peak change in the amplitude of the output waveform voltage, or simply the peak amplitude of the modulating voltage. The minimum peak amplitude of this wave is equal to the peak amplitude of the unmodulated carrier voltage minus the peak change in the amplitude of the output waveform voltage, or simply the peak amplitude of the modulating voltage. If the modulating signal is a pure, single frequency sine wave and the modulation process is symmetrical, then the percent modulation is derived as follows. Vm is half of the sum of Vmax minus Vmin, while Vc is half of the sum of Vmax plus Vmin. Then using the formula for the modulation index, we can derive the modulation index in terms of Vmax and Vmin of the AM wave. The peak change in amplitude of the output wave is the sum of the voltages from the upper and lower side frequencies. The peak amplitude of the upper sideband is equal to the peak amplitude of the lower sideband. Using the values of the Vmax and Vmin, the peak amplitude is equal to Vmax minus Vmin divided by 4. The figure shows an AM double sideband full carrier wave with 50% modulation. Notice that for a 50% modulation, the peak amplitude of the unmodulated carrier voltage is twice the peak change in the amplitude of the output waveform voltage. A 100% modulation occurs when the peak amplitude of the unmodulated carrier voltage is equal to the peak change in the amplitude of the output waveform voltage. Notice in the figure that the positive and negative minimum voltage touches each other, resulting in a zero minimum voltage. In 100% modulation, the carrier is fully modulated and the amplitude of the modulation is equal to half that of the main carrier, that is, the sum of the powers of the sidebands is equal to half that of the carrier. This means that each sideband is just a quarter of the total power. In other words, for a transmitter with a 10-watt carrier, the total sideband power would be 5 watts and each individual sideband would be 2.5 watts. During the modulation process, the carrier power remains constant. It is only needed as a reference during the demodulation process. This means that the sideband power is the useful section of the signal, and this corresponds to only 33% of the total power transmitted. If the level of modulation is more than 100%, this causes what is termed overmodulation. When overmodulation occurs, the carrier experiences 180 degrees phase reversals where the carrier level would try to go below the 0 point. The 180 degrees phase reversals give rise to additional sidebands resulting from the phase reversals. These sidebands caused by the phase reversal extend out, in theory to infinity, and can cause serious interference to other users if not filtered. Broadcast stations using amplitude modulation take measures to ensure that the carriers or signals for their transmissions never become overmodulated. The transmitters incorporate limiters to prevent more than 100% modulation. They also normally incorporate automatic audio gain controls to keep the audio levels such that near 100% modulation levels are achieved for most of the time. In this way, the signal sounds clearer and stronger when demodulated. The audio processor may also clip the audio if it becomes very close to the 100% modulation level. This will ensure that the carrier is not overmodulated.